Good morning, everybody. We continue our series of lecture recordings on different topics of deterministic and probabilistic elastic and elastic plastic analysis of earthquakes, soils, structures, and their interaction. Today is Friday, October 23. It's actually morning, 11:10. Today, we will talk a little bit about characterization of stochastic seismic ground motions. And joining me today is Mr. Wang.
Hello, good morning, everyone.
Thank you. Dr. Han Yang
Hello, how's everybody doing? Morning.
and Mr. Yusheng Yang, visiting student from Tongji.
Hello, good morning.
Good morning. So with this, I will ask Heshan to start. So Heshan, let's see if you can share your screen.
Yeah, sure.
Go ahead, please.
Yeah,
Great.
yeah, okay, yeah, yeah. So yeah, thanks, Professor Jeremic, for introducing. And so today we're going to continue our, talking on the stochastic ground motion modeling. Yeah. So for the for the stochastic ground motion, so basically we're going to characterize them as the time domain non-stationary Gaussian random process. Essentially, so the marginal distribution for most of the ground motion that we have been working on can be quantified by a Gaussian distribution, and the non-stationary here just means the the time evolving the mean, standard deviation, and the correlation structure is not stationary. And we're going to characterize such a random process using the statistics from the, the either from, there are two main components of the statistics that you need to develop. One is the statistics for the marginal behavior, the mean, the standard deviation, and also the statistics for the correlation structure. So so we're going to get these statistics of the uncertain uncertain ground motion by either, you can, in practice, you can select it a bunch of ground motion for your engineering objects, by either doing spectral matching or scaling or a bunch of all the other, ground motion selection techniques. And then, once you have all those, possible realizations of your ground motion, then you can develop those, the means, the standard deviation, and the correlation for the selected ground motion records. But from our, perspective point of view, for many scenarios, or for many, the seismic setting up that we care about, it's actually very hard to have enough to identify enough number of records for us to develop those mean reliable mean, standard deviation, and correlation. So actually, we also you can also do that. You can also develop those statistics from the simulated ground motion realizations. And specifically, we have been using the simulation techniques from the stochastic Fourier empty spectrum and the Fourier phase derivative spectrum to develop the realizations of the ground motion that is consistent with the seismic scenarios that you care about. And you can see those papers for your information. And so this is the so we are simulating some ground motions for, I think this is for a seismic scenario with magnitude 7 and the distance of 50 kilometers. And here we just show, actually we simulate, 1500. So here I just show you the first 200 realizations of the simulated ground motion. As you can see that, so when you considering this mean of this 200 realizations of the ground motion, actually the mean would be close to zero, because for any point they might be have the same chance to go to the positive and negative excitation. So they will just cancel each other. So you will end up with some standard deviation, also the correlation structure. And when you do the simulation of the ground motion, it's very important that you check the simulated seismograms whether they can consistent they're consistent with the current state of the practice of the GMPE. For example, in terms of the the behavior of the spectral acceleration. So here we are comparing the spectral acceleration simulated from the from the simulated ground motion with the GMPE of the NGOS2 database. As you can see here, yeah, yes, Professor.
No, no. So I just wanted to say, so GMPs are actually based on a large number of measured motions,
Yeah,
with this ergodic assumption. But so this is really checking. Yes, it is a state of practice, but it's really checking against measured motions. So we do simulated motions, but we actually check against measured motions, and this shows that the statistics is properly done, the
yeah.
statistical analysis is properly done, and these motions, these generated realizations,
Hmm.
are following the physics of GMPs.
Yeah, that's true. Yeah, as you can see here basically the mean, we are checking the medium is not biased, and also more importantly, we are checking the variability of the simulated, spectral acceleration. You definitely want to make sure you have the proper amount of the variability that input into your earthquake cell structure interacting system. And yeah, another thing that is also quite important, that is you can check for example, here we are taking all the accelerations at 20 seconds, and you can also check the distribution of those the marginal distribution of this random process, just to make sure it's properly Gaussian distributed. Yeah, I mean, to me, sometimes I do find, like, if your distance is very very close, like for near Fault motion, sometimes they show some non-Gaussian nature. So in that case, you need to be maybe need to be careful that the Gaussian assumption is still hold any is still valid or not. Yeah. But in general, for most of the cases, it is Gaussian distributed. Yeah. So
But
so in
can I ask a question? So if it
uh,
is not the Gaussian distribution, you can take that into account as well, right? You just have to change.
yes, yeah, you just need to use a higher order of the polynomial
Yes,
chaos. Yeah.
yes, yes.
Yeah. So this is the real easy DSL that we provided for you to characterize such a random process motions. So in our real easy terminology, we really do not distinguish the random field, a random process. So here we just generalize them as a random field. Essentially now the coordinate would be the temporal coordinate. So yeah. So here basically in this DSL command, you're going to need to provide the marginal distribution type, which can be either Gaussian, log normal, or gamma distribution. And then you need to provide the three files, the plain text file that specify the mean, the standard deviation, and the correlation. So the mean and the standard deviation, they are just a single column. You just specify, for each time step, what's the mean and the standard deviation. And for the correlation file, it's an array. It's a 2D array that is a full matrix of the correlation structure. And once you define such a random field, which is essentially a random process in time domain, and then you need to perform this Hermite polynomial chaos Loewe expansion with the specified dimension and order. And since most of the random process, they are Gaussian, so usually we only need to use the order one to accurately capture all the marginal distribution. And the most important thing is you need to choose the proper number of the dimension. So for example, here I have specified the correlation, the marginal mean, standard deviation, and correlation information in three text file, and I do the Hermite polynomial chaos Loewe expansion in dimension 115 and order one. And then after you've done this, you definitely need to check, whether your PCKL expansion capture the statistics that you're inputting. Yes, Professor.
So one note. So you go back one slide. So here you used the Gaussian distribution. Go back
Yeah.
one more slide.
Uh,
Yes. So here the distribution types can be Gaussian, log normal, gamma. We have a few more, right? We have Weibull
yeah.
and a few more. But you can, I mean, user can. So Gaussian is nice, and you need only go forward. You need only
Yeah.
one order one.
Oh.
No, no,
Order
forward.
one. Yeah.
You need
Yeah.
order one, but for others, you can do the same. I mean, you can use other distributions depending on what the data tells you, but you have to do this following step. Go to the next slide.
Uh-huh.
You have to go back and check how good your description, how good your statistical analysis is for given data. So go ahead.
Yeah, that's true. Yeah. So here we are just checking, the marginal behavior of the displacement and the correlation of the displacement random field that we are inputting to the system, and how that compare with the statistics that we are synthesized from our PCKL expansion. Yeah. So usually we find that for displacement random process is relatively smooth and easier to be captured, especially even with the correlation structure. But for the acceleration, it is has a lot of the it's much more transient, and the correlation structure is more complicated. So usually the dimension of the ground motion random process is actually controlled by the acceleration random process. And so here I have been showing you this is the correlation structure that we get from the the realization of the maybe the 1500 realization of the ground motion, and here is the correlation structure synthesized from our polynomial chaos expansion. And here I'm just to show you, what if you do not have the enough number of the dimension. So here you can see that, if you use only, dimension 15, you will get the correlation structure synthesized from the polynomial chaos, in this way. And this is the exact or the target correlation structure we want to match. As you can see here, if you use a lower dimension, so basically your random process motions will be more correlated than what the reality tells us. What the simulated ground motion tells us. So yeah, it's important to use a proper number of the dimension. And
If I may just add, this is very important step. Deciding on the PC dimension is very important, and this check always has to be done for motions, and we've seen this for the material properties, just to
yes,
make sure that you are using enough terms to represent your system in a proper way.
yes, that's true. Yeah. So once you have properly defined such a random process motion, and you do the proper number of the dimension order for the Hermite polynomial chaos expansion, then you can impose such a stochastic motions into the earthquake cell structure interacting system. So in Real-ESSI, we provide such a DSL command for you to impose such a random motion. So here there are several important information that you need to provide. For example, here you need to provide which node that you are impose this motion to, and also what the DOF, for example, either UX, UI, or UZ that you are imposing this motion. And also, so here the random field is the random process motion that you previously just defined. And the very important thing is that you need to also specify the penalty stiffness and also the double product. So here we are importing this motion as the stochastic random force using the penalty method. So usually we suggest you to use the penalty stiffness to be several magnitudes larger than the elemental stiffness that you are imposing the ground motion. And if you go to our previous lectures on the formulation of the stochastic finite element, you will see that in order to formulate such a stochastic force, you also need to provide a double product. So which is essentially a 2D array that you also need to be predefined, just like what we showed you before for the elastoplastic constitutive modeling. And here the order is also very important for this 2D array because it's not symmetric. So the first PC basis of this double product should comes from your PC basis of your uncertain displacement, which is essentially your global response polynomial chaos. And the second of the PC basis should comes from the random motion process, which is like in our previous example is that dimension 115 and order 1. So here I'm just showing you that the how do we define such a double product, and how we use this double product to define the imposed random motions. So essentially you just define two random field, the polynomial chaos basis of the two random field. So here we have been using the dimension 153 and order 2 for global displacement polynomial chaos basis, and then you can add a double product number 1 with this to define the polynomial chaos basis. And as I mentioned before, so sometimes this double product or triple product computation can be time consuming. So it's better for you to you can generate this double product, and then write this double product into HDF file and save it. And then next time when you want to use it, you can just load those double product from the HDF file. And then once you define this double product, you can impose those stochastic motions into the earthquake cell structure interacting system. And we're going to use this command in our next lectures to show you how do we impose these motions to do the stochastic wave propagation problem. So yeah, with that,
So
these are
so
some
so so
reference.
just
Yeah.
go back. So we're gonna provide examples for uncertain wave propagation with uncertain input motions and uncertain material for elastic. And then next lecture is going to be for elastic plastic. And then we'll provide those online so that people can try it out and just see
Yes.
how it goes.
Yeah.
Thank you.
Thank you. Yeah. Yeah. So thank you for your attention. And then I would just give thanks to my collaborators and also give thanks to the funding resources. And for more information, you can check our Real-ESSI website. Yes. Thank you for your attention.
Thank you very much. So we'll stop recording here. Let's see here.